In this video, I'm going to talk about the polar form of complex numbers. But first, let's think back to Cartesian form. So I'll build a complex plane. And in Cartesian form, we imagine there being a grid covering the complex plane. Now I'll add some number. And the way we describe this number whenever we talk about Cartesian form is how far do we walk along the real axis and how far do we walk along the imaginary axis. So for example, to get here, we would walk along this axis and then up this axis. And these have some lengths. So we would walk a distance 2 along the real axis and a distance 1 along the imaginary axis, and that gives us the number 2 plus I. In polar form, we're going to think of numbers as being described by how long they are and how much they've been rotated. I'll show you what I mean. Let's build a complex plane. And now we'll start with an arrow, initially pointing at the number 2. I want to point out that this arrow has length 2, which is obvious now, but we're going to rotate it, and the length is still going to be 2, so let's include that piece of information. Now let's rotate at some angle, and we'll assume that this is pi over 6 radians. Let's call the resulting number z. Now, a natural question to ask is, how do we write this number out explicitly? I'll first write it out in Cartesian form, and then we'll use Euler's formula to figure out what the polar form is. So first, note that there's a right triangle in here. But so that I have more room, I'm going to just imagine bringing this triangle down here. The hypotenuse is length 2. Here we have our right angle, and in here we have an angle pi over 6 radians. Trigonometry tells us that this side has length 2 cosine pi over 6, and this side has length 2 sine pi over 6. So to get to z, we walk 2 cosine of pi over 6 in the real direction, and 2 sine of pi over 6 in the imaginary direction. So this tells us this. This tells us that z is equal to, now I'm going to factor the 2 off the whole thing. Z is equal to 2 times cosine pi over 6 plus I sine pi over 6. And this part inside may look familiar to you. If we think back to Euler's formula, which tells us that e to the I theta is equal to cosine theta plus I sine theta, we can actually rewrite this as 2 e to the I pi over 6. When we write a number like this, 2e to the I pi over 6, we call it the polar form. And I want to point out that the length and the angle are represented right here by the coefficient and then this thing in the exponent. Let's go more general. Let's build our complex plane, and we'll start with an arrow, and note that this arrow has length r, and now we'll rotate at some angle, and we'll call this angle theta. Now the resulting complex number has 2 representations, re to the I theta or r cosine theta plus ir sine theta. Now the thing on the left we call the polar form, and the form on the right we call the Cartesian form. Now let's talk about multiplication, which is very nice in polar form. So if we had re to the I theta times se to the I psi, we get, well, r times s e to the I theta plus psi. This is much nicer than Cartesian multiplication, and we can even visualize what's going on with an example. So let's do 2e to the I pi over 12 times, this is going to be the first complex number, times 3e to the I pi over 6. So what we get is, well, we get 2 times 3 e to the I pi over 12 plus pi over 6. And that's equal to 6 e to the I pi over 4. Now let's see what's happening with our arrows. We'll build a complex plane. And now let's start with an arrow representing 3e to the I pi over 6. So we have this arrow, it's length 3, and I'm imagining it being rotated by some angle. Let's denote this pi over 6. So we'll start with pi over 6. And we're starting here. And for multiplication, I'm imagining this number acting on it to do something to this arrow. So what's going to happen? Well, when we multiply, you see we multiply the lengths. So we're going to multiply the length by 2. So we're going to stretch out here to 6. And then we have to add the angle. So we're going to rotate an additional pi over 12 radians. So let's go ahead and do that. So up here we have an additional pi over 12. And we added them together, and that's pi over 4 for the total angle in there. Now let's talk about division, which is going to be just like multiplication but going in the opposite direction. So in general, if we have RE to the I theta divided by SE to the I psi, well, this is just equal to R over S, so you divide the lengths, and then you do E to the I, and then you subtract the angle. And again, we'll visualize this via an example, but first let's go and do 6e to the I pi over 4, the number we ended up with last time, divided by 2e to the I pi over 12. So this is equal to 6 over 2, e to the I pi over 4 minus pi over 12. And that's equal to 3 e to the I pi over 6. Now let's visualize what's happening with the arrows. So we'll build our complex plane. And this time I want to start with an arrow representing 6e to the I pi over 4. So let's add that. And I'm going to think of 2e to the I pi over 2 as acting on this arrow, but this time via division. So what's it going to do? Well, it's going to rotate it back down pi over 12 radians. So we have a rotation like this. So that's this part in here. And then we have to shrink it down. So the 6 over 2 part is going to shrink the length down to 3. Now let's talk about how to perform addition and subtraction with complex numbers in polar form. So maybe you want to do r e to the I theta plus s e to the I psi. And you might be wondering, is there a nice intuitive formula for this? Unfortunately, no. It's actually terrible. And it's way easier to just convert the numbers into Cartesian form and perform the computation there than it is to think about trying to add numbers in polar form. So I'm going to go ahead and make a frowny face and say no. Don't try to do addition and subtraction when your numbers are in polar form. And that's where I'm going to end this video.